Hello, and welcome to another episode of Maths in an Empty Classroom with me, Mr. Southern. This video is about numerical solutions to equations using the Newton Raphson method. So what I'm going to start off by doing is just giving you a visual idea of what Newton Raphson is doing and how it works. So I've got a cubic function drawn on Desmos here. It has equation x cubed plus 2x squared minus 5x minus 4. And what I'm going to do is I'm going to use the Newton Raphson method to locate this root here at 1.856. Now, how the Newton Raphson method works is you pick a starting point. So I've got a little slider on here that a equals 4. So I'm going to pick my starting point that x is 4, and it's labelled up here at the point 472. And what you then do with that is you draw a tangent to the curve at that point, which I've done there. And you look at where that tangent intersects the x-axis, which I've just labelled on down here. So that tangent intersects the x-axis at 2.780. What you then do is you draw a new tangent at the point on the curve with that same x value. So x is 2.78 here. I found the point on the curve with x coordinate 2.78, and I'm going to draw a tangent in there and see where that one crosses the x-axis. And as you can see, that is crossing the x-axis closer to the x-coordinate of the root there that I'm trying to find. So if I label that one in there, that's at 2.13. What I'm then going to do is draw or find that point, or that x point, I should say, on the original curve. I'll just label that there for you. Pop a tangent in there, and that has now got very, very close to the root that I'm trying to locate. So if I pop it in there, you can see how it's pretty much lining up spot on with the root that I was trying to locate. And we've got a best estimate at this stage of 1.891. So that's what the Newton Raphson method is doing. It's starting at a point on the curve, drawing a tangent, finding where that tangent intersects the x-axis, drawing a new tangent to the curve at that x-coordinate, new tangent, new x point, and we do it as many times as required. It will not be more than 3 iterations that you have to do for your A-level pure exam. So you'll be pleased to know that there is a formula that computes Newton Raphson for you. And at the end of the video, I will show you where this formula comes from. But for now, we're just going to use it. So you should be familiar with the notation xn and xn plus 1 from your work with iterative functions. Xn is our current value of x, and xn plus 1 is the next value of x. So to get the next value of x, we do our current value of x minus f of xn, so subbing our x value into the original function, over f dash xn, subbing our x value into the differentiated function. So what I've got on my board over here is the equation of the original function, fx equals x cubed plus 2x squared minus 5x minus 4. And I'm choosing x0, my starting x value, to be 4, which corresponds with what we just did on Desmos. So first thing I'm going to do is I'm going to differentiate this function with respect to x and jot that down underneath. So f dash x is going to be 3x squared plus 4x minus 5. So that's all the differentiation I'm going to do for this question. The remainder of it is just plugging into this iterative formula. So I know that x0 is equal to 4. So to get a value for x1, I'm going to have to do 4 minus f of 4 over f dash of 4. And just for this first one, I'm going to write out a full written method of what that would look like. So 4 minus, and then on my numerator, I'm going to have 4 cubed plus 2 lots of 4 squared minus 5 lots of 4 minus 4 over 3 lots of 4 squared plus 4 lots of 4 minus 5. So subbing it into the original function, subbing it into the differentiated function. I'll just shifty that a little bit so that we're not lining up with those strange little predator eyes that I've got on my screen there. Look. So x1 is equal to 4 minus the numerator evaluates to 72 and the denominator evaluates to 59. And if I write that as a decimal to 4 decimal places, I get 2.7797 as my first approximation. So x1 equals 2.7797. What I'll just do is I'll just pop back to the Desmos. I've got it open again on another window here. So what we've done is we've looked at the point 472 where x equals 4. We've drawn the tangent in. We've looked at where that crosses the x-axis, and we've got 2.78 on the x-axis here, which is the same value that we've just achieved on the board here. Desmos has rounded it to 2 decimal places rather than 4, but there we go. Okay, so I'm going to do this 2 further times. I'm going to write a little bit less this time. So I've got x1 is equal to 2.779, etc. So x2 is going to be equal to that 2.779 minus the function evaluated for that number over the derivative of the function evaluated for that number. And something that in, that comes out to 4 decimal places as 2.1301 to 4 decimal places there. Okay, let's pop back over to Desmos a sec. So what I've done then is I have found that point on my graph where x is 2.78, drawn in the tangent and looked at where that tangent has crossed the x-axis, and it does so here at 2.13, which is the x value that I've achieved on my board here. Okay, let's quickly do x3 then. So we've got x2 is equal to 2.1301. So x3 is going to be 2.1301 minus 2.1301 subbed into the original function over 2.1301 subbed into the differentiated function. And to 4 decimal places, that comes out as 1.8914. So just pop back onto Desmos then, and we'll just do that last one. So we've got x is 2.13. I found that coordinate on the original function, drawn the tangent in, and found the point where that tangent intersects the x-axis. And there it is, 1.891, which is the same number that we've achieved on the board here, which is good. Okay, I'm going to show you where this comes from, but I just want to do a quick thing on Desmos here to show you situations where the Newton Raphson method might fail, because this is something that you've got to be aware of. So the Newton Raphson method can fail for a number of reasons. One time it can fail is if you draw the tangent in and it moves further and further away from the curve. That's not going to happen for this one, but what I can do is if I move the value of a, so you can see how if I start closer to the route that I'm trying to find, I get a better estimate more quickly, which should make sense. But if I carry on moving it to here, where I'm at the turning point of the curve, the Newton Raphson method is failing here because drawing the tangent to the curve at the turning point, then that line is not going to intersect the function near to that route again. So that's an example of when Newton Raphson method would fail, and it might be that you're asked a question about that in the exam and given a picture, but that would be the limit of what you'd be asked to do. It's more likely that you have to do the process of what we've just done on screen here. Okay, last little bit then is, well, where does this come from? Well, bear in mind that we have been looking at tangents. When we find the equation of a tangent, we use the general equation of a straight line, which is y minus y1 equals m bracket x minus x1. Now, if I just think about this in terms of what we are doing here, well, if I write it as y, y1 is going to be f of x1, which is this x1 here. What I'm just going to do is pop that in as xn, because then we've got f of xn here. Now, my new x coordinate is going to be this one here, xn plus 1, and my gradient is going to be f dash xn. So I differentiate at this point x, I find y at this point x, and that would be finding my equation of my straight line. Now, because I'm trying to find the intercept with the x-axis, then actually y equals 0 here. So I can rewrite this, and I'll do it a little bit bigger. F of xn minus, also equals f dash xn bracket xn plus 1 minus xn. And if I rearrange that, I end up with this formula. So if I start by dividing by f dash xn, I get f of xn over f dash xn is equal to xn plus 1 minus xn. And if I add the xn over, I get xn minus f of xn over f dash of xn equals xn plus 1. There we go. I don't believe you have to know the proof for that, but I think it's interesting. I think it's cool to see why it works. So there we go, Newton Raphson method. This formula is given in the formula book, so you've just got to know how to use it, and that's how to use it. Thank you very much for watching, if indeed you still are.